In this scenario, we have our friendly user Pete, who's a big basketball fan. Just like me, he loves basketball, but he also doesn't like staying up late, so he misses all the West Coast games late on into the evening. So in this case, Pete has walked into his office, fired up his browser, and he wants to check on those scores and see what teams beat what other teams. Now he types ESPN.com into the URL address bar into his browser, and he's presented with the screen you see here. Now, last time I checked, ESPN's webpage looks a lot better than this. So clearly we have a problem. It looks like in this case, none of the images have loaded associated with the website, and maybe even the style sheets have not loaded completely here as well. So there's clearly a problem, and our goal here is to look at the packets and figure out what the problem is, and particularly where the problem lies. Is it a problem with Pete's machine, or is it a problem with an upstream system, maybe with the ESPN web servers or content delivery servers themselves? So let's pivot over to Wireshark, and we're going to look at the file http espnfail.pcapng. In the packet capture we're looking at, Pete captured it while he was browsing to the ESPN website from his local machine. So that's the perspective we're looking at here in Wireshark. And you'll immediately notice there are quite a few more packets than we're used to in some of the other exercises we've been looking at in this course. Down here at the bottom you see there are 569, and that's because this is more of a realistic capture. I've taken care to not contaminate it with things that are unrelated to the scenario, but still we're not looking at a specific protocol feature or function here. We're really digging in on a practical scenario, not unlike something you would see in the real world. Now, what that means for us is we can't just simply scroll through these packets and expect to be able to figure stuff out. We have a lot of conversations going on here. They're not always entirely sequential. We have a lot of things interwoven together. So just because packets appear next to each other in this list doesn't mean they're necessarily part of the same conversation, and so on. So we can't really do that. We have to really rely a bit more on our analysis skills and some of the analysis features that are part of Wireshark. And that's great. That's exactly what we want to do, and that's what I want this exercise to do as well. Now, what do we know about the scenario? We know that our user is browsing to ESPN.com and they're not receiving back all the information they would hope to get back. We're missing images, we're missing style sheets, we're missing important components that allow the website to render correctly in our browser. Now, since we know this is an HTTP issue, one thing that might help to start off with, and what I would do, is try to summarize the HTTP communication that I'm seeing. And there are a few ways to do that, but I think the way I'm going to start is by going to statistics at the top and going to HTTP and then requests. So that's going to actually show me all of the requests made by host. And we see that listed here, and those hosts are expanded to show the URIs. So we see here, it looks like we have 7 requests to a few different hosts, ESPN.com, ESPN.go.com. It looks like we have CDN.optimizely.com. We also have a couple other CDNs here. We see ESPNCDN.com listed here with a couple of subdomains. So when we see a CDN listed there, that's a content delivery network, and many of these sites, they don't host all the content on one single server. The reality of the modern web is that content on any given web page is going to come from a variety of places, so you have to keep that in mind. Now, the one thing that does look a little bit odd to me when I look at this is I would expect to see actually quite a few more requests when I browse to ESPN.com. It's got a whole lot of content on there. If you browse to that website on your computer right now, you'll see there's a lot of things going on. There's a lot of different subdomains, different ads, third-party content integrated into the page, social media integrations, things of that nature. And I don't see that here. 7 is not enough. So clearly that's indicative of a problem, although that doesn't on its own tell us where the problem lies, or specifically if it's something HTTP related. We don't have enough information to go on that here. So with that said, we have to keep looking elsewhere here as well. Now, one other thing we can do, now I've chosen to pull up the HTTP analyze statistics window to look at this data. We can also look at it here in the main window too. There's nothing to say we couldn't do that. So I can actually go in here and let's do an HTTP request method of GET. We're going to look at all the GET requests in this capture. And we see the same number of things we saw before. So there are 7 GET requests here, which is what we'd expect. That's consistent with the HTTP statistics window we just looked at. Now, which one should you use on a given basis? It's really personal preference. I often will use for smaller captures where I know there's fewer number of them, I'll use this screen. But if there are a lot of them and I really need to summarize, especially a lot of specific individual requests per domain, I'll use that statistics window we just looked at. But this is a way to start by looking at these HTTP requests. Now, since we're looking at all these GET requests, one thing that might come to mind is look at the responses to the request to see if anything looks out of place. So that's what we're going to do here. I'm going to go ahead and click and get rid of this request method filter that I have. We're going to go ahead and filter on HTTP response code. So this is going to show us every packet that has an HTTP response code in it. And that's what we see on the screen here. Now, the first thing to note is that there are 7 of them. We had 7 requests and we have 7 responses. So that means we don't have any requests that necessarily went unanswered. Now, beyond that, we see we have 6 OK responses, which from our work analyzing HTTP data, we know that means that the resource was delivered OK. The server responded with the data that was requested. And we see 1 HTTP 301 moved permanently. That's perfectly normal. And matter of fact, it's the first thing we see. So probably someone requesting the document root in this case and getting redirected to another specific location. That location is espn.go.com, which is highlighted down here in the packet details window. So everything here looks fine. There's nothing that looks out of place. We have the same number of requests and responses. We don't see anything like 500 server errors or 403 forbiddens or 404 not founds. Anything that would indicate that there's something wrong with the HTTP communication, that the client was making an improper request, that the server was unable to handle a particular request for some reason. None of that's here. So we don't really have a reason to believe that there's any problem with the HTTP protocol present in this capture. Now, that said, there are a couple other protocols we can look at. So let's start thinking about where else we can look to diagnose this problem. To figure out where we want to go next, it helps to get an understanding of what protocols exist in this particular capture file. Now, here we knew that we had HTTP because that was the nature of the problem, so that's where we started with. But now I want to know what else is there. So I'm actually going to go to statistics and then protocol hierarchy to get a breakdown of all the protocols that are available. Now, when I look at this, I could be tricked into thinking this is all there is, but there's one thing important to note. And remember, we looked at this when we looked at the protocol hierarchy window early on. Note down here that this is based on our display filter of HTTP response code. So it says 100% of the traffic in this packet capture is HTTP. And that's actually not true. That's because we're based on that display filter. So I actually need to go here and close that. I'm going to go ahead here and get rid of the filter. And then I'm going to open up the protocol hierarchy window again. And now things are a lot more realistic. We see we actually have other traffic going on there. Now, in this case, it looks like all of our traffic is Ethernet traffic, which is pretty much to be expected. But we also have, at this point, beneath IPv4, we have UDP traffic and TCP traffic. Now, it looks like all of our TCP traffic is HTTP, at least as far as application layer protocols is concerned. But we also have some DNS traffic, and that's of interest. That's another layer 7 application layer protocol that we can examine to see if anything looks awry there. And it looks like there's not a lot of it. Matter of fact, it looks like there are 14 packets. Now, if I wanted to, I could go ahead and just go ahead and right-click on this, apply a filter, and let's just apply a filter for DNS, which is a pretty simple filter, right? It's just the word DNS. And that's going to show us all of these DNS requests and responses. There are only 14 of them here, so it's not too tricky to go through those. It looks like Pete's workstation, 172.16.16.154, is making requests to 4.2.2.1, which is his DNS server. We see our initial request for www.espn.com, and then we get a response. We see another request, and we get another response, and then we see several other requests and responses, 14 packets. So it shouldn't be a surprise we have 14 packets here because remember we visited 7 different domains we saw when we looked at HTTP data. So 7 domains, that means 7 requests and 7 responses. 7 plus 7 is 14. So DNS data at a quick glance looks fine. I don't see anything that leads me to believe there might be something wrong here, which means we need to look elsewhere to continue to troubleshoot this problem. We've exhausted the application layer protocols we have to work with. Of course, now we have HTTP and DNS. And we've kind of looked through both of those and didn't see anything that looked immediately troublesome. So let's go ahead and look at something a little bit different and move our way down the OSI model and actually look at conversations. I find looking at just a list of conversations a good way to understand the flow of traffic and to kind of understand what's going on. Now, in this case, we see we have our conversations window, and it's divided into a couple different sections, as we've seen. We have 16 TCP conversations, 7 UDP, and 8 IPv4. And we're already open here to IPv4, and notice that there are 8. And that's a little weird to me. That's interesting because everything thus far we've seen has come in sevens, right? We had 7 different HTTP requests. We had 7 DNS requests, no doubt identified by these UDP streams over here. But we have 8 IP conversations that are going on, and that's just a little weird because it's not quite lining up with the 7 we've seen. So that means perhaps we have a scenario where something is trying to talk to something else, but not getting a response, and maybe that's happening at the IP layer. So that's why we're not seeing any weird DNS or HTTP traffic, because maybe that's not getting that far. So let's look at this and dig in. Now this is sorted. It's a default sort right now, but let's actually go ahead and sort it. Let's start by sorting it by bytes, putting the most at the top. So we have our top talker here, which looks to be 72.246.56.35, talking to Pete's workstation. This 172.16.16.154, and it's responsible for 196K of traffic, and it looks like it's bidirectional communication. We have 134 packets one direction, 113 the other direction, and so on. Now, of interest here, if we look at these columns, this packets A to B and packets B to A, and scroll down, we see we have bidirectional communication everywhere except right here. That's odd. We have 93 packets going from A to B, but we don't have any packets going from B to A. B in this case is the remote IP address, this 203.0.113.94. Well, that's odd, so I think we should dig into that. To do so, I'm going to right-click it, apply as a filter, select it, and we want the bidirectional communication, although we know that traffic is not occurring in both directions. Now behind us, we see what we have going on here, and it looks like we actually have Pete's workstation sending requests to this remote IP address, this 203 address. We see several SYN packets being sent, TCP SYN packets. Now, if this were a normal conversation, what would we expect to see? Well, we would expect to see a SYN ACK, and then we would ACK, and then we could perform normal communications. And of course, this looks like it's over TCP port 80. We see that listed here. So we would expect to see probably an HTTP GET request, maybe a POST, but probably a GET to retrieve additional content. But it doesn't look like that's happening. So we have these several, looks like 6 SYN packets, and then we have a bunch of retransmissions. It looks like the same packets getting retransmitted over and over again. Looks like here at packet 534, we have another set of new SYN packets being sent to try to establish a connection, and then several more retransmissions. So this process is kind of repeating. And in this case, if you look at the source and destinations, we never get a response from 203.0.113.94. So something is amiss here, and this device is not responding to the requests that are being made from Pete's workstation. So let's think about what the missing link here is now that we've kind of identified some things that may be connected. We have, in this case, 7 legitimate requests we've seen, right? We saw 7 DNS requests and 7 HTTP requests that are all matched up. We know those are related. So now we have this 8th conversation going on. So what's missing? Let's think about how an HTTP request works. If I want to communicate with a host via HTTP, I'm generally going to have a domain name. I'm going to generate a query, a DNS query for that domain name to find the IP address. And once I have that IP address, I'm going to make my HTTP request over IP using that IP address. In this case, this mysterious 8th request, if it had made a DNS request as well, a separate one, we would generally probably see another DNS request, right? We wouldn't just have 7, we would have 8 of those as well, but we only have 7 DNS requests, and you can go through this and look on your own, but you'll see in all of the answers to those 7 DNS requests, none of them have 203.0.113.94. That does not exist elsewhere in this packet capture. So that means our system, Pete's system, is actually requesting this, trying to connect to this 203.0.113.94 address without actually having done any recent DNS query that we've actually examined. So why is that happening? Well, in this case, we don't actually know based upon the packet capture alone. We don't know why that's happening. All we know is that it has happened. Now, there are a couple theories that come to play. One is that for whatever reason, that DNS query has already happened. So we missed it. It was happening before this has been captured, and it's been cached. So if you remember, the way DNS works is that the local system will check its DNS cache first to see if an IP to domain mapping exists, and if so, it'll use that information instead of requesting another one and generating more network traffic. In this scenario, I'll tell you that's exactly what has happened. Is that DNS request happened some time ago, and that entry was cached, so you don't see it made here. Now, the problem has occurred in that the infrastructure on the ESPN side of things has changed, and the content delivery network server that contains the images that are missing in this case were related to this specific domain name associated here, to this 203.0.113.94 address. So that address is actually changed, that DNS mapping has changed, but because the local system has an out-of-date DNS entry, it is unable to actually reach the system, because it is unable to get the new query and query the new information and get the appropriate IP address to request the data. Now, how would you fix this? Well, a couple ways. One is that DNS entry has a TTL and will expire at some point, at which time the machine should force a new DNS query to get the new IP address and information. You could also manually do that DNS query on the local system. You could purge that cache. And that's not to say that there might not be an error somewhere on the ESPN side that fed this system the bad IP address. But for this part, I'm going to expect that the issue is probably on Pete's workstation, and that he has this out-of-date DNS cache entry. So hopefully that all makes sense, what we have going on here. It may help to step through this again on your own if you haven't already, and I certainly hope you have, to see exactly what was going on with this failed connection. This was a really great example of using Wireshark's different statistical analysis features, actually looking less at packet contents and more at the counts of packets and the numbers of packets and where things don't match up, to really understand the interplay between all these different protocols that are encapsulated together. So we just had, in this case, a missing DNS query that meant we were able to hone in on that, look at the extra IP conversation we had, and that led us to find these retransmissions and these SYN packets that were never responded to. So hopefully that makes sense to you. Again, if it doesn't, go through this, step through it, and if you have questions, be sure and ask those as well.